from, for these products can vary from tens of TOPS to hundreds of TOPS. So as we address this wide range of the design roadmap, the custom AI processor, how do we avoid designing a processor specific to each product so we can leverage one design that can be adapted across all these products? So at the heart of all this is really AI processor. We call it NPU core. It is unique and designed for high performance and leverages a lot of the energy efficient technique that we learned from our bubble space. And really scaling from the small device, like the AI pin, all the way to the data center, we scaled by increasing the number of these cores. So that's one way of scaling. So we repeat these cores. For example, in the data center, we have chips that have 16 of these cores, and we have 4 chips per card. That gives you 64 cores, and then you multiply by number of cards, so it gives you a huge number of cores that you can work with for much bigger workloads that you can deal with. So the significant advantage here is that we use actually software across the board, the same software, and basically that code allows us to deploy products very quickly for the same model accuracy. So that's kind of the big leverage that we get by using this core across the board. So to keep this NPU core architecture performance going and adapting and trying to track AI evolution, we need tools to analyze bottlenecks for executing evolving AI workloads and accelerate the hardware changes. So another area of scaling that we look at, since we play in the mobiles with all these different edge devices, multimedia is a very important area. One example of multimedia is camera. So across a lot of this AI spectrum of products, basic camera and display blocks are similar, but the requirements vary different in camera count, speed, and power. For example, for like mobile, you could have between 3 and 5 cameras, depending on the tier of the mobile. In drones, for example, we need fewer features to save size and cost. In automotive, you need maybe 20 plus cameras, and that requires computer vision assisted by AI, so you can, with very low latency and real-time decisions. With XR, it's wearables, have about 12 cameras, and the even more stringent requirement for power and latency. So even though we can leverage the core IP blocks, like ISP, image signal processing for camera, and display across all these devices, to meet the diverse requirement and cost targets, currently we often create separate architectures and hardware design variants for each case. So the key question is, can EDA help us build one flexible architecture that adapts to these diverse requirements instead of manually customizing for each time? So that's a key one, and we've been thinking about this problem for a while, and hoping we can get to a solution soon. So adapting IP from like one product, for example, actually before I get to that, just at safety, automotive is another area that that actually creates a lot of interesting work. Automotive has safety requirements. So adapting all the core IPs that we have to automotive products, we need to add safety hardware. And tools are needed to optimize the trade-off, satisfying safety standards and increased cost. So adding the FUSA, the functional safety RTL, pretty much eliminates possibility of using the physical implementation from the previous designs, leading to manual effort design of the new floor plan. So that's a lot of rework that we have to do because of the safety thing we added. So finally, we must check for safety coverage, and although some tools exist for fault injection to assist us in that, manual review is required. There are no automated sign-off tools. So it's an area that we spend a lot of effort just adapting the existing IP to automotive. The next set of challenges is SoC integration. So when we want to bring all these SoC very quickly, take all these IPs and build SoCs. There's a lot of manual work as well, so we'll go over that. So let's look at that process. So like I said, we designed this one technology roadmap that's scalable, that's adaptable architecture for the individual IP cores that can be customized to the different AI products requirements. So the challenge still remains in implementation of the SoC variants. For for different AI products. For each product segment or market tier, the RTL must be verified and the cores must be integrated into silicon. So even though a lot of functionality is common across the product segment, the lack of effective SoC integration tools result in significant human effort again. So again, you're going to hear this theme over and over again as we go through all the different efforts that we go through in designing these products. So to understand the cause of human effort, let's take an overview of the SoC design process. So the architecture and RTL changes to retarget an IP from one product spec to another triggers floor plan changes. So the floor plan changes triggers system validation, triggers design verification and resynthesis. And floor plan change and resynthesis triggers physical design, and then depending on the form factor changes the product, and it triggers mostly package redesign. So EDA tools today are inadequate to support architecture and RTL changes or floor plan changes, and these are done manually today. So some of the tools exist to analyze RTL that can help guide the changes, but design expertise and reasoning are still critical to make these changes. This is actually a very important point. So we still need the designer expertise and reasoning to make all this work. Even though the tools are evolving and getting better, but we still have the experts to be able to close those designs. So while tools exist for devious synthesis and figure design and package design, they cannot achieve the product targets without considerable design expertise and numerous design iterations, which means a lot of effort, means a lot of time to get to the end result. So definitely opportunities exist in EDA and AI to increase design efficiency, PPA, and reduce AUC. Let's see an example to understand the magnitude of this challenge. So let's say initially we may have a base RTL for a given IP, for example, a mobile product that we'd like to adapt to another product requirement like automotive, for example. So this may trigger some RTL changes. Finally, the modified RTL must be implemented in silicon with the process we just described. So a given IP, let's say a camera, so it can be reused for a new product with no changes to RTL, but the changes in another IP core, such as the NPU, can trigger a whole new implementation effort. So even mainly involving floor planning, effort will mainly involve floor planning to accommodate changes in IP core, changes in EDA tool, recipe for synthesis and physical design, and timing closure for sign-off using manually guided iteration for the EDA tool. So even though there's an IP that exists, because of that change, it creates all this huge effort. So the tools, again, are inadequate to make incremental changes without significant human effort and reasoning skills to iterate. So, and as an example of the overhead of the simplest of these tasks, let's say the recipes tuning, let's look at two SoCs with common IP and different floor plan. So, floor plan for a given AI product, called product A, you see on the slide. For a new product, due to changes in the AI workload requirement, for example, the core IPA needs to be expanded and increased, so it needs more space. So as a result, in the absence of floor planning tools, the designer used spatial reasoning and moved the core IP marked IPB to the top middle to the right middle to allow the IPA to grow. So the designer estimated that it should be possible to squeeze the IP cores on the left of IPB. You see with the arrows there. So let's look at the impact of that squeeze that happened on IPC. Since the right-hand boundary of IPC was squeezed left, its internal block 1 no longer fits in the new space. So the designer used the geometric reasoning skills to reshape the boundary of block 1 to fit in the boundary of IPC. So while the reshaping of the block in IPC, the physical design tool cannot meet PPA, power performance area targets, in the first iteration, and results in severe congestion as shown in the slide. So on the first pass, with the ADA tools, it appears that the revised floor plan would not work. Note that the RTL and length list of this block have not changed, and the only shape and boundary change here in this case. So using this special and geometric reasoning, the several iterations with EDA tools, the physical design engineers were able to achieve the targets with the same netlist and floor plan. So these iterations took about 3 months with a huge team iterating through the design. So that's obviously unacceptable. That's a lot of effort. So the designer intuition was correct. By getting the EDA tools to meet the PPA targets with this floor plan revision, it took multiple iterations, and that's what caused the 3 months effort. So the 3 months were spent in recipe tuning of the EDA tools. Neither the RTL nor the floor plan were changed in these iterations. So this is a huge source of inefficiency. I know that EDA tool companies have AI-aided fine-tuning that's happening, but that consumes a lot of compute. So further innovation is needed for this task, so tools can really reason like a physical design engineer. So manual efforts significantly increase our NRE, so that goes without saying. That's something we're trying to minimize. So how can we develop tools that can reason like a physical design engineer and converge on the physical design without the lengthy time that it takes today? So another example of inefficiency with current EDA tool is technology node porting. Sometimes we have a product and we want to take advantage of a new tech node because we get power benefits and we get area maybe. So we don't want to port that to the new tech node. So the human designer effort to adapt to such a change can cost also a lot of time, and that's a huge effort. So innovation is needed for tools that can accommodate technology porting. So let's automate that process. So that's very, very important area because we do a lot of these tech node, where it makes sense, and having a tool or an agentic workflow that allow us to take advantage of that very quickly is definitely something we'd like to get. So in all these examples, there was no RTL change, so just mostly floor planning and shape of the IP core. So when the RTL, for some IP changes for specific market segment, the design engineer expense also persists and requires a lot of human effort to go through that. So the current EDA tools are not adequate to reduce the DV and integration effort for RTL adaptation. So we need tools that can learn from the designer, reasoning embodied into the past design, so I take advantage of the past design and reduce the NRE for new products where only a fraction of the design is changing. So if we had tools that can learn from the previous designs and only limited change in the RTL, then these tools can do a lot of the work for the engineers. So the next area that we spend a lot of effort in is package and testing. So that's another huge effort that we go through. So let's take a look at that. So even in mobile, for example, there's more DOU, day of use need to increase, like you have your battery can last longer. So one question that gets asked, is increase the battery size. And also sometimes also the number of cameras, as you guys notice, it seems like they're adding cameras every few years to these phones. So the SoC gets squeezed, and there's limited really place for the electronics, and that sometimes necessitates to repackage some of the products and change the packaging. As part of that, another area, before I go there, another area is for glasses, for example. The arms of the glasses are very thin, and we don't want to make those any thicker because you want to have a slick and stylish product so you get a high adoption. So you don't have a lot of space to work with. So the SoC, as well as thermal and power characteristics, will be much tighter than mobile, for example. So even if it's economically viable and technically possible to integrate into a single silicon, we don't want to do that because you might want to have to system to split in multiple die so you can use the whole space on the arms of the glasses. So in doing all this work, there's interesting trade-offs that need to be made between thermal and power delivery network. So today, package designs rely on serial analysis to balance thermal and PDN trade-offs. So the placement of the core IPA in the center to dissipate the thermal it works for thermal. However, if you look at the capacitor on the upper right, it's quite a distance from the IPA, and that distance, leads to increased. It basically impacts the PDN performance. And so if you look at, if let's say we move the IPA closer to the capacitor, then you get much improved, by shortening the electrical path, you get improved PDN, but then you have also worsened the thermal dissipation. So these kind of trade-offs are currently evaluated manually and for each use case. So a multi-physics co-optimization tool that can simultaneously analyze thermal and PDN effects could significantly reduce human effort and identify optimal IP placement that meets both thermal and PDN specs within the die constraints. So today, thermal analysis and PDN analysis tools work independently, and the designer must go back and forth to optimize the design. So another area is due to form factor changes, for example, and thermal dissipation. Sometimes the same SoC must be packaged differently. For example, vertical stacking of the SoC and DRAM must be modified to a side-by-side topology to improve and reduce the Z height. So changes in topology results in longer routed channels, and full signal integrity and power integrity analysis and optimization is needed. So minimizing the design time and effort, what we need is really a parametric tool that can sweep topology options and auto-generate eye diagrams to check for the signal integrity and power integrity. So another trade-off for vertical stacking is really we must make is the die thickness. So thicker the die are better for thermal, but cause higher bump stress. So a lot of effort is spent iterating of the optimal die thickness. So we need tools that automatically optimize between thermal and mechanical design. So all these things take a lot of human efforts, and that's why I'm kind of repeating this, because we need to find ways to automate a lot of this. So another area for in-package architecture design, as shown here, for the vertical stack, if we move the DRAM to the side and place a heatsink, improves thermal but affects signal integrity. So we need a multi-physics analysis that can jointly analyze and optimize cross thermal, mechanical, signal integrity, power integrity, and PDN cross-package variants. So currently, the tools are needed for each domain, and the serial process of going back and forth again increases the turnaround time and the effort. So this is another pretty important optimization area that we need to focus on. So innovation is needed in the tool for every design step, as shown here. So we need tools to analyze architecture and RTL to identify bottlenecks to meet new specification and generate changes needed to meet spec. For fork planning, we need tools that can take the changes to some core IP or block and figure out how to rearrange and reshape the core IP blocks to accommodate the changes and converge in physical design. For DV, we need tools for root cause analysis and debug. Currently, language reasoning models are limited to test plan generation, so there's definitely improvement to be made here from the AI front. For synthesis and physical design, we need tools for recipe optimization and time enclosure that can reason like a physical design engineer and converge in one iteration, hopefully. For packaging, we need advances to jointly optimize cross-thermal, mechanical, and PDN. So in all the EDA tools, with all these tasks, we need advancement to really achieve significant reduction in runtime and compute. This is also the cost factor also is super important. So finally, we need innovation in Gen AI. A Gen AI that can create design input for the EDA tools, like a human designer to drive fast convergence, and agents that can orchestrate design flows to reduce human effort for iteratively running tools to refine and optimize the design. These are critical technologies to rapidly adapt common hardware to evolving AI product demand. So we need innovation in AI for SoC design. So the textual reasoning that LLMs use to successfully analyze and optimize software code is fundamentally inadequate for analyzing and optimizing hardware code like RTL. So AI models need to understand the impact of the code on the timing and physical design and implementation. So for timing, the models need temporal reasoning from code, and for physical design, they need spatial and geometric reasoning on code. So, and then for DV, root cause analysis and debug, language reasoning on the RTL code is insufficient without really temporal reasoning, so that identify the source of timing error, for example. So new foundation models and agents are needed that have all these 4 reasoning skills and can learn from the expert hardware designer. Again, learning from the expert hardware designer, that's really the key for all this. So such model can then customize and adapt existing designs to new product requirement in the compressed time that we have. So at Qualcomm, our researchers are working very hard to try to figure out how to solve these problems, and working with a lot of companies out there, and we're aware of a lot of very, very interesting startups that are looking at this space, as well as the EDA companies that are looking at how to improve all these processes. So we hopefully will see more engagement going forward. So to recap, it's really, AI is not just another workload, it's redefining the entire design space. So we reuse IP, but we cannot efficiently adapt it. So we understand the right architectures, but we cannot converge quickly. So our engineers have the intuition, but our tools cannot capture or execute their reasoning. So the bottleneck in AI innovation is no longer silicon capability, it's really the design productivity. And our best engineers can reason and figure out the solution, but it takes months for the tools to realize it. So that is not a scaling problem, it's really a reasoning gap. So closing this reasoning gap requires fundamental shift in design automation. So we need tools that don't just analyze and optimize, we need tools that learn from the hardware designer how to reason. So this will lead transformation of EDA, going from design automation to design intelligence, and then from design tools to design agents. So this is not just about building better tools, it's really about redefining how we design silicon in the age of AI. So hopefully I gave you kind of a little bit, a hint of what the things we're struggling with at Qualcomm, and I'm sure it's equally true for a lot of the companies. And hopefully we can work with the community and find ways to allow AI to take care of a lot of these tasks that are human intensive, so we can have our engineers focus on the creative work in designing new products. Thanks for your attention, and have a great day. Thank you.